Okay, welcome back. So I'm going to go into the first of our three different ways of proving or ways of finding the acceleration here. I think I may have bled out a little bit, too much outside of the frame in the last video, so hopefully that wasn't too bad. Anyway, so we've got this idea here of position space, which is sort of your ordinary space, where you have some your position of the object in question is represented as vector r, and then velocity here is which way the object is moving. So really what this is velocity, if you'll recall, is the rate of change of position. So over here, I'm going to say velocity is rate of change of position, which is our r vector. Okay. Well, over here, this is velocity space. We're sort of we're setting this up as though velocity itself is position here. So we're finding this center here, and then we're taking a circle that's always, the magnitude of velocity, or all the points are a magnitude of velocity different, and we're just moving around this circle as the velocity changes. So at this point right here, the object is over on the right side, the velocity is pointing up, and it's going counterclockwise. Here the velocity is pointing straight up toward this point on the circle. So what we want to find is something analogous here. What's the rate of change, I'll abbreviate that since we're close to the edge, of velocity. And that, I think we ought to know that by now, that is acceleration, is the rate of change of velocity. Does this mean that we can take the acceleration vector and draw it up here the same way we drew velocity here attached to the object, showing which way it's moving? Can we draw an acceleration vector up here, pointing that way, showing which way the velocity is moving? Yes, we can. So this is really analogous here to to the way the velocity is sort of pointing around the circle for position space, because it's as though velocity is like this arrow tugging on the object, telling it where to go. Well, here it's like your acceleration vector is tugging on your velocity vector, telling it where to go. So it's this weird sort of almost trippy analogy where you're in an alternate universe almost, where velocity is position and then acceleration is velocity. So it's this kind of weird, it's like people being, people saying, oh, what if we could see smells, man? Wouldn't that be so weird? It's kind of like that. Okay, so what we want to find now, to complete the first of our proofs here, is we want to find how long it takes for this velocity space vector to go around. So how long does it take the velocity to sweep all the way around and come back to its starting point? We're going to call that period t. And so t, well, recall what we did over here to find out how long it takes to sweep up this circle. We took the distance around the circle and divided by the speed you're going around the circle, right? Distance divided by speed. Well, here you do the same thing, but we're in this, remember, we're in this trippy world where distance is actually sort of measured like in units of speed, and then speed is measured in units of acceleration, or dimensions of acceleration. So our distance around the circle, well, the circle has a radius of v, right? So v is the magnitude of our v vector. So this, the radius is equal to the speed. So we can just say here 2 pi v is our distance around the circle, right? And then what's the speed we're going around the circle? It's actually a, our acceleration, magnitude of acceleration. So this is the period to go all the way around this circle. Now, what does this period, the time it takes to go all the way around this circle, have in common with the time it takes to go all the way around this circle? And it's not hard to see that they're actually the same. When you start over here, you've got your position over here and your velocity pointing up there. Well, here you've got your velocity pointing up, acceleration pointing that way. And then say when this thing gets around to about, say, up at the top here, positions like this, velocity is like this. So at that time, the velocity is going to be over this way, and then acceleration is going to be pointing down. And then a little later, when the object is over here, it's going down, so velocity will be down then. And you can just follow this all the way around and see that you get all the way around a circle in the same period of time. So this period, I'm going to switch to a different color. How about this nice little sort of lavenderish color? So this period and this period are the same. So because they're the same, we can take these two expressions on either side and equate them. So 2 pi r over v equals, let's make sure I got space, yeah, 2 pi v over a. Okay, well now we're cooking with fire. So 2 pi and 2 pi on both sides cancel, right? So there's a v out here, sorry. So what we get there is r over v equals v over a. And at this point, there's a lot of different things you can do with this to manipulate it. But the version we like best is where we take acceleration and multiply both sides by a to get this side out. And then I guess multiply both sides by v to get this v out, and then divide by r. So what we get out of this is a equals v squared over r. And you can wrap that up in a present and send it to grandma because it's done. This might not be a mathematically rigorous proof, I don't know, but it seems to me to be sort of drop dead easy, simple, and I almost think it must not be mathematically rigorous, or else people would use it more often. But I really like this way of saying it. So what this is saying is that your acceleration is proportional to the square of your velocity, and then you divide by the radius. And so one way you can look at this intuitively, just before I finish this video, is what happens if your velocity, say, doubles. Okay. Now, if you look at the math and your velocity doubles, then you're going to have a 2v getting squared, right? And so that's going to be a total of 4v squared. And so acceleration becomes 4 times as much. So if your velocity doubles, acceleration becomes 4 times as much. Math, that's easy to see. But can we make sense of that intuitively? Okay, so let's think about what it means up here. Here we keep the same radius, but we double velocity. So suddenly this thing is going in the same circle, but it's going a lot faster. It's going twice as fast around. So what does that mean? First of all, it means if you come over here, this vector becomes twice as long, which means this circle here gets to be twice as big. So imagine this circle here expanding and becoming twice as big. All right. So now, to get around, if the period were to stay the same and this circle just got twice as big, it means that to get all the way around, you'd have to be going twice as fast, right? So there's one sense in which you get a doubling of acceleration. Well, okay, so you have to go around twice as fast, and your speed here in velocity world, in velocity space, we're calling it, is the acceleration, right? So to go around the twice as big circle in the same amount of time, you have to be going twice as fast. But then also, what else happens? Well, over here, your period, if you double velocity, your period gets cut in half. So you're going around the same circle here, but you're going twice as fast, which means it only takes you half as long. So translate that over here. Now you're going around this, we already established this circle is twice as big, and now in addition to it being twice as big, you've only got half as much time to go around. If you're this velocity vector, you've got to spin around that in only half the time, and you got to go twice as far. So that's another factor of 2. So it's like half the time multiplies the acceleration by 2, and then the fact that it has to go twice as far multiplies by 2 again. So that's how you get that squared dependence out of there on sort of an intuitive level. So that's it. There are 2 other proofs which will be forthcoming in the next 2 videos if you want to see them. If not, feel free to just skip ahead.